if we look at a basic structure of an atom, we really have three pieces. Okay? And I would argue we can kind of ignore the nucleus as a piece because it's really just a sum of pieces. But we really have three pieces. Okay? A few people have had me all the way back for Chem 130, so I apologize for a little bit of repetition so you can avoid answering this question. The rest of you have a more interesting question to answer. What does a neutron mean? What does a proton mean? What does an electron mean? Yes, they're all subatomic particles, but what does it mean when I say I have a proton? What do you guys think? If you had the slides, you could cheat and look, but the idea is don't do that. Okay? We could reference a charge potentially out of it. But I haven't said anything about the presence of electrons. So you're right, a proton is positively charged, but all I've said is, here's a proton. I've told you no other context. If added context there's no electrons, I now know that that thing is positively charged. Okay? But all I've said is proton. What does that mean? So to get charge, I need another piece of information. All I know is proton. What do you mean it identifies the element? What element would it mean if I have proton?
Hydrogen.
Hydrogen. The number of protons identifies the element. So as soon as I know the proton, I know the element. Okay? So that's useful information. Okay? Because we started to go down that path, what if I tell you hydrogen and one electron?
Hydrogen and one electron, or hydrogen with
Hydrogen and one electron. I understand your and statement, but these things are associated with each other, yes. We now know it's neutral. Well, what was the difference between positive and neutral? What are we referencing?
charge.
The charge. So the number of electrons identify your charge. We don't get electrons existing on their own. They're tied to an element. They're tied to the protons. Once we've defined the element, we know the protons. By now defining the electrons, I can define the charge on said element. Okay? What are neutrons? Okay, so hydrogen atom, neutron. Again, associated with each other. Okay. Deuterium is just another name. I want something else.
Hydrogen 2 isotope?
So if I said oxygen and a neutron, what is getting defined now by the presence of that neutron? The mass. That mass, if it's a common enough isotope, we associate a different name to it. Okay? But really the identity of your neutron or the presence of that neutron tells you the mass. If it's a common enough, fancy enough isotope, now we'll name it. So we add an extra layer of information on top. So when I go through and look at protons, neutrons, and electrons, that's what I use to define them. Okay? Your protons and neutrons are located in the nucleus, and our electrons are located in orbitals, okay? Outside the nucleus. Organic chemistry is about ultimately carbon making compounds. So carbon has to interact with another atom. What is the most likely thing from carbon to interact with another atom?
Electrons.
Why the electrons?
Because they're on the outside.
That's it. So when we're talking about organic chemistry, we're talking about how carbon's electrons interact with the world around it. Done. We can all go home. Okay. Good, you didn't get up. Okay. That's what we're primarily concerned about. So some of the issues within that is how do we define those interactions? Okay, what's going to cause those interactions? Which of carbon's electrons are going to be important? Because when we look at carbon, is it just one electron? No, it's 6. Okay. Why 4? Valence electrons. So of those 6, are all 6 equally important to me in determining how it's going to interact? No. I'm more concerned about the outer shell, because the outer shell is the most likely thing to interact. Right? Just like when you interact with a person. You're probably going to make up all sorts of goofy stories about like how your name was created, and it may have nothing to do with the truth. Right? But it could be a fun little story that everybody starts to believe things about you. Okay? You may hold back the truth. Okay? That interior part until you've made a stronger connection. Okay? So when we're looking at the interactions between atoms, we're going to stay primarily focused on the electrons, and we want to know about those outer electrons first. Okay? Well, are all of those 4 outer electrons for carbon equal? Do they all occupy the same space?
No.
No, why not?
Some 2 are in the s orbital, 2 are in the p orbitals.
That's where they are. Why are they not in the same space?
Because some of them are higher energy and some are lower.
Why are they different energies?
They're both negative, they repel.
Like charges repel. I don't put all 4 electrons in the exact same space because those electrons are going to repel away from each other. The exact same thing happens in the nucleus. Why do we not necessarily care about the nucleus?
Nuclear force from the neutrons.
Because it's OChem, and I don't care about the nucleus. I care about the electrons. If we go back to GenChem, why are those protons now allowed to stay there? The neutrons come in to affect it. Okay? And act as a glue to bring them together. So what we're really trying to look at is those fundamental pieces, and now how do we slowly scaffold that extra information in? Okay? Back in GenChem, we looked at those electrons, and we looked at the orbitals they were in, and we could look at orbital diagrams. We start with a nucleus. The very first energy level we call 1. The second energy level we call 2. This is an insanely complicated nomenclature system. Okay? That's what those numbers mean. They're just referencing the energy levels. How many energy levels are we concerned about? It's a hard question because it's kind of subjective.
I mean, are we talking in organic chemistry?
So we could classify, let's just say chemistry in general. How many energy levels do you think we're concerned about?
7.
Why 7?
Because you can't make anything with the same energy level and you found anything.
When we look at chemistry, what is our key for chemistry? The periodic table. And each of the rows on the periodic table is an energy level. When I go through and look at it, there's 7 rows on the periodic table corresponding to the 7 energy levels. That's why they're there. Okay? Organic chemistry is going to be a little bit different because we don't care about all of those rows necessarily. Okay, why not? We're concerned primarily about organic molecules, and the organic molecules tend to be centered around carbon, which is located only in the 2nd row. So my focus tends to sit there. Okay, and that's where most of our chemistry really sits. Okay? As we move up in energy, what happens? Our energy levels split, and we get degenerate energy states. Okay, where we get different orbital types. We get S and P. Okay, for the 2nd energy level. I started to hear a whole bunch more. Does the 2nd energy level have D? No, I'd have to move up to the 3rd energy level, right? Okay. Why do we not want to look at the 3rd energy level as organic chemists?
Because carbon isn't going to interact there. Carbon doesn't have one. Well, I should say that.
S and P. What is the shape of the S orbital?
Sphere.
P orbital.
Dumbbell.
D orbital. That's why we don't look at the 3rd energy level. Okay? As soon as we bring in that 3rd energy level, we bring in the D orbitals. The D orbitals are vastly more complicated and require different theories to go through and explain them. Organic chemists are too narrowly focused that we don't want to have to evaluate the complexities that come with those D orbitals. Okay? It was originally created to build simple molecules. That's where we started. Okay? Once people mastered that, they started to scaffold higher into the higher energy levels. Okay? So, we would get all of our electrons, and these orbitals we would reference as the atomic orbitals. And we could look at pictures of these atomic orbitals. Okay, we've got our spheres and our dumbbells. And we've got these representations behind them. Right? All fair review? Okay. The problem with these atomic orbitals is what do they apply to? Atoms. And what is organic chemistry about? Compounds. So as soon as we scaffold up to compounds, this atomic theory goes a little haywire on us. And we have to come up with different models to mimic what happens in molecules as opposed to atoms. So we end up learning a whole new process for how these things combine and come together. Okay? So this builds our periodic table. This is organic chemistry. We don't deal with really the d orbitals, so we could immediately get rid of them. Probably none of you are going to deal with the f block, so we got rid of that a long time ago. Okay? So we get rid of the d block, and we really just have s and p. Notice within this periodic table, what else have I chopped out? I really only have 1, 2, 3, 4 energy levels. Chopped out the 5th energy level. Arguably, I shouldn't have done that, because there's one element in the 5th energy level we should probably look at. Iodine. Iodine will show up fairly frequently as well. Okay, so we've simplified what we have to do with periodic table. Gen Chem, you got to deal with that whole freaking beastly thing. This is why we do OChem. It's easy. Less stuff to worry about. Okay, but that's not it. Because there's still a bunch of junk up there I don't want to have to worry about. So what does OChem go through and do? Deletes it. And our focus for OChem is largely centered across these atoms. Okay? To a little bit of an extent, we also deal with sulfur and phosphorus, but those are primarily going to show up in second semester. Okay? They just kind of kick in as a random, here, look at me thing in first semester. Second semester, we have to worry about them. Okay? So that simplifies our life a lot. So we're dealing with s orbitals and p orbitals. And for the most part, those p orbitals are centered in the second energy level. Okay, so these are now all roughly the same. Okay? Are there other patterns in the periodic table that you learned in Gen Chem that we might want to consider in OChem? Electronegativity. Okay? So we do have the discussion on orbitals already. Right? Hopefully we remember those first two columns are our S block. These last ones are our P block. So getting at where those electrons are located. We could look at electronegativity. Okay, what is electronegativity? A measure of?
Attractiveness to electrons.
Attractiveness to electrons. Wrong.
How readily it is
give up electrons?
How ready it is to give up electrons. Wrong. The two definitions that were both given are, one is for ionization energy and one is for an electron affinity. Neither of them are electronegativity. What is electronegativity? It is related to ionization energy. So what is different about that definition? Since you're staring at a screen, I'm guessing you're reading it from someone? Yeah. What is different about the definition of it takes electrons versus it takes bonding electrons? It has to be in a compound. We're talking about electrons coming from a bond. When we look at electron affinity, it's taking electrons from the vacuum, from nothing. Okay? Those are drastically different principles because in one case there's nothing else there, in the other case something else is there. Okay? We could talk about your ability to grab money off the table. It's probably pretty good. Okay? Is your ability to take money out of somebody else's hand as equally good? Okay? No, it changes the dynamics of everything. So electronegativity does a slight switch on us. Okay? What is our trend for electronegativity? Fluorine is the most electronegative. Okay? The symbol for electronegativity is typically Chi. or a weird looking X. And then, because we've simplified our periodic table, potassium would be the lowest electronegativity. So electronegativity is useful on our periodic table. We need to have that information because we can use electronegativity to predict trends. We're talking about how two molecules interact with each other, or ultimately two atoms interact with each other. And even further, how the electrons of those two atoms interact with each other. Well, what is electronegativity? Which atom wants to take the electrons away? That's organic chemistry right there. Okay. What's another trend that you could find on the periodic table? Size. Okay. This is usually a fun one because almost everybody screws it up, so it's cool. Okay. Where is size on the periodic table? Okay. I'm going to make an argument that there's two trends for size. Okay. So I see a lot of people doing little triangle, or not triangle shapes, but a lefty-right thing. That's two trends. You got one up, down, and one left-right. Okay. So pick the one that you're most confident in and just run with that and hope 50-50 you were right.
Size goes up as you go towards fluorine. Or
Okay.
towards the right.
Okay, so
Size decreases as you go right. Yes, yes.
size decreases as you go right. Okay. I'm going to make the argument for organic chemistry. Wrong.
I think it increases down.
Okay. So now we have two options because we had a guess out there and mine was, you're wrong. Technically you're right, so that's a good job. But it doesn't apply to OChem. Okay, because that differential in size, left to right, isn't that big a deal. Okay. So the other suggestion is going down the table. Man, that is a horrible color. Let's try that color. There we go. Now you can see it. Going down, what happens to size? It increases. It gets bigger. So when we move down a column, we get a significant difference in size. Okay, why do we get a significant difference in size? More electrons. That is an awesome answer. I love that you said it, primarily because you're wrong. Lithium to fluorine, what happened to the number of electrons? There's more electrons, and yet the size got smaller. So when we go down a column, and it's awesome that you're doing this. I absolutely appreciate it, and because people are like, oh, dude, he's totally ripping on people. Do it. We need to have that conversation because I guarantee most of you were saying the same thing. Electrons also increase down a column. Real quick attempt at a recovery. There's more protons left to right. There's more protons down a column. Still doesn't work.
It's because the forces that are attracted to each other, so it's going to shrink because there's more positive and more negative charges compressing the shell.
There's more positive and negative charges up and down the column, so I don't quite accept that. Going big enough and saying, oh, it's the forces that do it. Yeah, you're right.
You're adding more energy shells as you go down.
It has to do with where the electrons are located. Down a column, where are the electrons located? The outermost electron for fluorine is located where?
The 2p.
It's in the second row of the P block. That outermost electron is 2p. Chlorine, 3p, 4p, 5p. The energy levels are getting further and further from the nucleus, okay? Because they're higher in energy. That's why the size gets bigger down the column, because the electrons are going into a higher energy orbital. Left to right. Lithium, the outer electron goes where? The 2s. What is the energy level for the electron for lithium? Rhymes with poo. It's 2. Sorry. That's all I had. Okay, it's not S. S is not an energy level. S is an orbital type located in that energy level. Where's the outermost electron for fluorine? 2. The electrons are going in to the exact same energy level. which means what should the size do? Nothing. I'm putting the electron at the exact same place. Size shouldn't change. That's the organic approximation. And it works really, really well. Why does the size actually decrease? And now we can go back to your refinement on your answer. When we move left to right, not only are the electrons going in at the exact same location, what are we also doing to the nucleus? We're making the nucleus stronger by adding protons. Because the electron is located the same distance initially, stronger nucleus, that sucks it in a little bit tighter. Okay? That's now a very subtle effect, which is why left to right in OChem, we don't even worry about size. They're all the same. Kind of makes sense? So as you're going, I hope I don't ever have to remember this again. All you have to remember is the trend. Do you worry about size across a column? Or across the left to right thing would be a row?
No.
No. When do you worry about size? Up and down. Okay? Electronegativity. What's our trend? Okay? Up and to the right. So electronegativity, we need both. Okay? Ultimately, what we'll find is that electronegativity and size contradict each other. They contradict each other in such a way that size will dominate as an answer so long as we're within a column. Because left to right, there's no size difference. Okay? So size becomes very important and the first thing to evaluate, so we look to see where they are within a column. Electronegativity is now going to be only within a row. How else could we, looking at this periodic table, acknowledge that electronegativity is really only going to be important across a row? How many columns do we have?
2.
Really just 2. Okay? We have the first one and the last one as far as our simplified periodic table. We really only have 1 row. That 1 row is our electronegativity. Kind of, sort of? Cool. So we've now taken all of Gen Chem with that giant, massive thing on the board, and we've boiled it down to 10, 15 elements. And some simple trends that you need to memorize. Do you need to memorize those trends? Yes. Do that. Because you can then apply those trends. And that's going to become important. All right? So there's those statements. When we talk about atoms to compounds, we're taking 2 atoms and we bring them near each other and we generate an interaction. Okay? The result of that interaction is going to dictate what we get out of that. Okay? We could get an interaction where what happens?
Ionic.
What's that?
Ionic. Are you talking about different types of ions? Or?
Eventually getting there, yes. So, yes, but too good. Don't be so good.
So sharing
We could potentially be sharing electrons.
or stealing?
Okay? Or we could not be sharing electrons, but are now weakly attracted. Or, so if we think about this, you walk up to a person and have an interaction with them. You're now either married or you're dating.
Or you're fighting.
Our third option is that what do those 2 atoms do? They repel each other. Okay? Depending on which of those states we get different explanations. Okay? If they become married, we're looking at bonds. If they're only dating, we get, I think it was you. What'd you give me earlier? No. Forces. We get bonds and forces. Ultimately, bonds and forces are the same thing. They're an interaction. It's just a strength of the interaction. The stronger the interaction, the more likely it's a bond. The weaker the interaction, the more likely it's a force. Okay? Or there's 0 interaction and they just repel away from each other. Okay? So we really get those 3 kind of common states that come out of this. And ultimately, all of that is coming down to what those electrons decide to do, and primarily those outermost electrons. Okay? If we get that really strong interaction, we get a bond. If we get a weak attraction, we don't get a bond, we would get a force. Okay? The other variations between it are all bonds the same? No. What bonds do we have? We have covalent, we have polar covalent, and we have ionic. I would argue that covalent is the best way to reference it. Most people usually add an extra word to that, being nonpolar, to distinguish it from polar covalent. So we get those three primary types of bonds. Okay? Do we have different types of forces? Yes, good answer. What are those forces? London dispersion forces. Dipole, dipole. What's that? Hydrogen. Usually call it ionic. Sometimes you'll hear it referred to as electrostatic. So we can now classify those two kind of separate. We have a strong interaction or a weak interaction. Okay? So when you look at a compound, you should be able to tell me that it's nonpolar covalent or a covalent bond. What are you looking at to tell me it's a covalent bond? Give me a nonpolar covalent bond.
Carbon-hydrogen, single bond.
Give me another one. And don't tell me another carbon to hydrogen single bond.
It's carbon-carbon.
What about those two allows me to say they're nonpolar covalent? Okay, so I was fishing for a keyword and I got that keyword, and then a couple other people shouted out good answers. Electronegativity. How many of you have memorized the electronegativity of either carbon or hydrogen? That definition sucks. Nobody wants to memorize electronegativities. Don't. Okay? So we need to come up with a hand-wavy rule that allows us to come to those classifications quickly. That classification, same atom to same atom, and carbon to hydrogen. That's it. Those are now nonpolar covalent bonds. How do you know you have a polar covalent bond? Everything else. Because I think I heard that shout out. It's a good answer. Is sodium chloride same to same? No. Is it carbon to hydrogen? No. So do I accept everything else yet? No. Because sodium chloride would not be a polar covalent bond. It would be an ionic bond. So what makes it ionic?
It's a metal and a non-metal.
Okay. Metal and a non-metal. What you could be doing is referencing origins of the name. Covalent assumes nonmetals to nonmetals. Okay. Which is why we could get away with the everything else. Everything else as a statement really only works because you've defined ionic and just straight covalent. Okay? Is it perfect? Absolutely not. Does it work 90% of the time? Probably 99% of the time, yes. Okay? The next part is what happens with the forces. Okay? I would love to get into that right now, but I'm actually going to take a step back away from the forces, because that ultimately, to try and mimic your ability to read, all of the forces fall in Chapter 2. Okay? So we'll come back to those. You at least acknowledge that you knew what the names were. That's awesome. So we're going to go back and look at the bonds. Is there a theory to explain bonding?
Yes.
Yes, good answer. What would that theory be?
Vesper.
Vesper's not bonding. Lewis. Okay? You've all seen Lewis, right?
Yeah.
Draw the Lewis structure. And don't. So I've got 3 rough approximations of answers that I've seen scattered around. Okay? This is one of the problems dealing with OChem and why we spend a lot of time talking about Lewis structure, and I put that 1-hour video out there. Okay? Lewis structure is a hard concept to deal with. There are millions of shortcuts to sneak through it. right? Or just outright ignore it. So depending on your faculty member or the amount of time that you decided to devote to it, you may not have nailed it down in Gen Chem. Unfortunately, you have no choice. You need to know Lewis structure to get through this class. Everything we do is based off of structure. You have to have a solid understanding beginning to end through the entire process. Right? To start off, when we look at this structure, your first step should be, and I didn't see a lot of people showing this first step, determine the number of electrons that go into your structure. If you don't know the electrons that go in, you can't draw the structure correctly, which means looking at your valence electrons. Sulfur and oxygen both have the same valence, so I'm just going to say 6 times 5. The charge, to have a -2 charge on a molecule, what do I need? I need more electrons, which means I'm going to add 2 more electrons to this. And I have to somehow represent the presence of 32 electrons. Okay? Within that 6, I'm ignoring all of the core electrons. Because in Lewis structure, we're trying to simplify things and only look at the most likely things to interact. The next step is arguably one of the next most difficult ones. How do we decide to arrange those atoms? Okay. Gen Chem, we tried to set it up where you had a clear central atom and the rest of the atoms then go around it, okay, which is where you would get to these 2 potential answers. And I'm not going to like that arrow, so I'm going to erase the arrow right away, but that's how you get those 2 answers. If you don't know, you may be putting them in a sequence or a straight line. Okay? When we move further into OChem, we won't be able to follow the rules outlined in that video. We have to start making some approximations and probably moving towards something like arranging the atoms in a line, okay, and doing shifts off of it. But that requires having done enough Lewis structure with a center atom to recognize those patterns. Okay? That is a challenge that we'll have to work with. Okay? So that straight line one is unfortunately wrong for this one. The next part that I very commonly see as an answer would be this one, which I'm going to scream about for what reason? Where are all the electrons? Okay? So what you have done by drawing this is you probably implied the presence of lone pairs around. Okay? And believe it or not, by doing that implication, you're actually on your path to becoming a very good organic chemist, because most organic chemists imply them. However, we imply them because we know we're implying them. You're implying them because you're lazy or you forgot. And it's true, it's not a big deal, because ultimately that's why chemists do it too, is we don't want to draw them because we're lazy. Okay? Everything we're talking about this semester and ultimately second semester is the movement of those electrons. If you don't draw them, can you show them move? Okay, that becomes difficult. So you should be drawing all those electrons. Okay? This on its own is technically a bad answer, but usually one I would accept. Officially, we'd have to draw a -2 on it. This is where Chem 130 should have gotten you. How many people think that is a correct Lewis structure? Oh, really? That is an absolutely valid and perfect Lewis structure. There is nothing inherently wrong with that. Okay? We've satisfied all the rules that are necessary behind it. 151 should have come along and said, there's more information that you can put in that structure. Instead of saying the -2 charge is somewhere in the whole structure, it is actually on specific atoms. So we would have to calculate a formal charge. A formal charge is calculated by doing what? Like that. Formal charge equals valence electrons minus non-bonding electrons, and I'm waiting for someone to drop in the last hammer on this one.
Minus number of bonds?
Cool, I like that. Number of bonds. You may have heard someone reference minus half the number of bonds. That's a Gen Chem carryover on being insistent on units. We don't need to stress so much about the units. Okay, valence electrons minus non-bonding electrons minus the number of bonds. Oxygen has how many valence?
6.
6. How many non-bonding electrons on that oxygen?
6.
6. How many bonds? 1. The charge on that oxygen? Minus 1. Well, if that one's a negative 1, what do we have for all the other oxygens? They're all negative 1. Should I be seeing some negative in my structure?
Yes.
Why?
Because you have a negative structure.
Sulfate, negative 2 charge. Okay? But we have 4 negative charges. That doesn't add up, right? That's because we didn't do sulfur. When we go through and do sulfur, what are we going to find its charge comes in to be? A positive 2. This is also a valid Lewis structure with slightly more information to it. 151 should have said, you're not allowed to draw this because
You've got a positive next to a negative.
that'll work. More specific than I would have said, there's charge. We want to minimize the charge as much as possible. Okay? So we will minimize that charge. How do I cancel a positive charge? Combine it with a negative. What made the negative negative? Electrons. What made the positive positive?
Oh, wait.
So protons isn't a bad idea, but remember OChem, I don't care about protons. What makes the positive positive?
Lack of electrons.
The lack of electrons. This one has too many, this one has too few. What can I do? I can share them. Okay? So for those of you out there that immediately drew double bonds, one of the questions that I would then ask would be, why did you draw a double bond? And usually the answer I get is, because it's supposed to. Or Google said that. Or the textbook shows that. It has a double bond to cancel the charge. That's why. That is the only reason we're making a double bond in this case. Double bonds don't just appear. There's a reason for their existence. That reason is usually to satisfy octets or to balance charge. Those are the only two ones that you need to be concerned about. Okay? So cool, we've minimized some of the charge. We could do it again and have some more electrons come in to make a new double bond. We'll lose the charge there, and we'd end up with our structure for sulfate. This is now one of the more widely accepted structures for sulfate. 151 should not have stopped there, but it may have. What is the problem with that as an answer?
That's not the only possible structure.
There are multiple ways that we could have canceled those charges. I could have taken the electrons from the bottom oxygen to make the double bond here. Okay? That representation of that structure now becomes quote-unquote different, because when we go through to draw Lewis structures and address the concept of resonance, we have pinned each of the atoms in that position. There's no, I'm rotating the structure. There's no rotation of the structure. Didn't happen. Right? Each of those oxygens is independently identifiable. Okay? Which is why when I draw out the Lewis structure with the double bond here and here, that is now a different structure because I have a double bond to the blue atom and a single bond to the red oxygen. Okay? Those are now separate resonance structures. Make sense? So when we're going through and doing Lewis structure, your textbook's going to have you do a whole bunch, and they're usually central atom based. You have one atom as the center, you then scatter the rest of the atoms around it, and you draw a Lewis structure. And the idea is that you would draw enough Lewis structures that you would pick up common patterns. We don't do that in Gen Chem because how many common patterns are we going to find when we have to use every single element? That's going to suck. But for OChem, oh my gosh, it's whoa, it's still wet. Okay, that was a bad idea. We don't use every single element. That's why we can do it. The amount of bonding patterns that you have to deal with are now vastly simplified. Okay? So the idea is that you should do bonding patterns for boron through fluorine. Okay? And hydrogen. How many bonds will hydrogen have? 1. Lithium is underneath hydrogen, which means lithium acts like hydrogen, which means it reacts similarly, which means how many bonds does lithium have? Sodium. Lovely. Okay, I'm going to skip magnesium because that's really second semester. We could go through and do the same thing for our boron, carbon, nitrogen, oxygen, and fluorine to come up with the typical bonding patterns that we see for them. When we vary outside of those bonding patterns, we know we have to address either charge or lone pairs, and sometimes charge then too. Okay? So you have to do enough practice to nail that down. When I took OChem, it was like 100 stupid questions, and it was ludicrous and dumb, and I hated it. Okay? And it was only till afterwards when I started working with students, and students being like, well, I can't draw a Lewis structure. Well, how many Lewis structures were you made to draw? 5. There's your problem. Okay? So you either memorize those bonding patterns, or you get it beaten into you by doing enough Lewis structures with those atoms. Make sense? Okay. I'm giving you the option. I'm not going to beat you over the head with Lewis structures. Okay, so let's advance a whole bunch there. So, my rules behind how we draw them out, okay, it's a lot of rules. They end at the exact same answer, which ends up being the problem with Lewis structure and probably how you were taught. You can get to the answer, but you don't know why you got to the answer. All you're doing in Lewis structure is placing electrons. Well, what is OChem about? Moving electrons. If you don't know why you placed the electrons, you have no context for how you should move them. That's why OChem becomes difficult, because you have a bad fundamental understanding of how the electrons exist. Okay? That's why I have these rules and these patterns. I would recommend you follow them when doing Lewis structure practice. Believe it or not, you can go back and do any Lewis structure you want. These rules work. I've had a couple people like, those don't work. They didn't work because you didn't follow the rule. Okay? Every single time. Okay? So, the next part that can come out of this, because I said this one was an okay structure. How do we decide best structure? Okay? Because when we go through and draw Lewis structures, we may encounter multiple different representations for that compound. Well, which of those representations is better? Well, if the charges are all the same and the octets are all the same, well, they're all the same, and then you have to draw all of them. But you could encounter situations where maybe it's not quite perfect. You can't quite figure it out. Okay? There has to be a rule set. For assigning your best one, you have to satisfy octets. Okay? So when we go through to place electrons, I'm just going to outright erase this because this is a common one. We followed our rules for drawing out our Lewis structure. Okay. We need to place electrons as our second step for this. Where does my first pair of electrons go? Shh. If anybody heard him, no you didn't. Where do the first pair of electrons go? Okay. So we had two answers, going to the oxygen and going to the most electronegative atom. In this case, both of those statements are true. Okay? You should always place them on the most electronegative atom. Okay? Typically, I would place them where I know there needs to be some. If this is a compound, those have to have a bond. I'm going to place my first pair of electrons there. Where does the next pair go? No. This is going to be one of those jerk instructor moments. And
The same.
preferencing. Literally just had the rules up there. Didn't you read them?
There's a bunch of them.
Come on.
That's what octet for.
I want to satisfy the octet for that atom. Since I'm choosing this oxygen to start with, I'm going to place my first pair of electrons in that bonding space, and then I'm going to satisfy the octet for that oxygen, which means the next pair goes on the oxygen, oxygen, oxygen. Which is an octet. How many valence electrons does oxygen have? I don't care. Okay? It is entirely irrelevant. Why is it irrelevant to placement of those electrons?
Because you're in a compound.
It's a compound now. This is a molecule. Valence electrons are irrelevant. We total the valence to get our valence, and now we scatter those electrons across the molecule. It's a potluck party. Okay? You bring cake and I bring shredded chicken. Okay? That doesn't mean when we start the party, all I eat is shredded chicken. And all you eat is cake. We divide that mass up across. Does that mean you and me are going to eat the same amount of shredded chicken and cake? Probably not. I'm a little bigger than you. I'm probably going to eat more than you. Okay? How do we quantify my stomach versus your stomach when we talk about atoms? Electronegativity. The ability to hold those electrons. Oxygen, being the most electronegative, is going to get its food first. It's getting its octet. The next set of electrons, the next oxygen. The next set of electrons, the next oxygen. Which one? Doesn't matter, they're all the same. Okay? I only care about valence as the very first step to figure out how many electrons to scatter across the party. And I care at the very end to decide how overweight your instructor is going to be after the potluck. Okay? I don't care about anything through the middle. Make sense? This analysis allows me to get to resonance and dealing with these other concepts quicker. Okay? So I will always satisfy the octet rule. The next one, minimize charge. Are there other ones? Yes, you typically don't have to worry about them. Okay, so we just looked at sulfate. Why would we exceed the octet for sulfur? Because I'm minimizing charge. Why am I allowed to exceed the octet on sulfur?
Sulfur is in the third period, so it's got to be orbital.
Third period, d orbital, expanded octet. There's more space for electrons. Why do we typically not have to worry about that in OChem?
Operate in the second period.
We only operate in the second row, so we don't have to worry about those expanded octets. Okay? So let's take a look at another example there. CH3CO+. All right? How many electrons does carbon have?
6.
4 valence. How many carbons are there? 2. Electrons from hydrogen. 1. How many? 3. Oxygen. 6. 1. 6. We have a charge of a +1. What does that mean? I need to subtract 1 electron. Okay? Because all I'm dealing with are electrons. If we do that, I believe we get 16, right? Okay. This one becomes a little bit more difficult. Okay? We're now scaling up into OChem a little bit here. How would we know how to arrange those atoms? Is there a clear center atom? We'd use carbon. Okay, so I'm going to do carbon. Sorry, that was an eraser. Carbon, hydrogen, 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 carbon, oxygen. Well, that's kind of weird. Let's fix that. Oxygen, carbon. Clear, well, no, why not?
So you're going
When
to very rapidly exceed carbon's octet, and you can't
Okay.
do that.
And you can branch off another carbon.
By doing multiple Lewis structures, you learn the bonding patterns for each of those elements. The bonding pattern for carbon is 4 bonds. I can't have a central carbon be a center atom because that would mean 5 bonds. Okay? Could I have done something along, oh, come on. Oxygen, carbon.
Yes.
Yeah,
But it's ugly.
it's fair game. But it's ugly, okay. So somebody else elaborate potentially on why you think it's ugly.
Isn't carbon usually using bonds?
But like we said, we can't have carbon be 100% a central atom. Okay? So we have a carbon that arguably is central, and we'll have one that's non-central. Why is this structure ugly?
Wouldn't you have to do like oxygen?
Because of carbon.
Prove it to me.
Would it have to do something with the octet?
You got 16 electrons.
2, 4, 6, 8, 10, 12, 14, and then carbon doesn't have a full octet.
Right? How many electrons do I got?
14.
Yeah?
Yeah.
Let's make some bonds. Should not be using that as an eraser. Some of you have been like, this is just looking uglier and uglier. You didn't give me a valid reason for why it was ugly. If you can't give me a valid reason, we gotta just power through it.
Would it be because of the type of bond?
Okay? So we get a couple different answers that can come out of this. Okay? We've put in all of our electrons, which means we can't put in any more. Okay? Carbon doesn't have its octet, so what could we do?
Triple bond oxygen. Put carbon in the middle with no bond in the middle.
You?
Have we satisfied octets?
Yes.
Your argument for the octet being invalid is not true.
Would it be because
Okay, now the formal charge is horrifying.
Minimize formal charge. So we could go through and evaluate formal charge, and it's going to be not pleasant. Okay? What we'll get here is an oxygen at a +2 and the carbon at a -1. Okay? Should you be that fast at it? Probably. You don't need to be that fast. Don't stress yet. Okay? Okay? A charge larger than 1 is questionable. Like, that's probably a bad idea. So what does that mean about how I placed those atoms? There's probably a better way. This is where OChem becomes challenging, at least initially. You now have to figure out what is the better way to arrange those atoms. Okay? This is one of the reasons why Gen Chem ignores this subject. Okay? And if you did that Lewis structure lab in 130 or 151, I have massive objections to it because you run into a lot of issues like this. Okay? And you will get a faculty member saying, you are wrong for this answer. Did they tell you why it was wrong? Well, when you look it up, it's wrong. Irrelevant. Did I follow the rules? Yeah. Okay? It absolutely works. Why is it wrong? Like, holy shit, he drew that fast? Yeah. A little bit of practice. Okay. There was another way you could have arranged it. In that other arrangement, what happened to the amount of charges?
Lower.
They're lower. That makes this top drawing better than this bottom drawing. How do you as a student know you should be drawing this top drawing and not the bottom one? Oh, it sucks at the beginning. Trial and error. Okay? Eventually what we do is we say, I know that was bad. I shouldn't have asked you to do that. Look at this formula. Carbon is bonded to the 3 hydrogens. What's the very next atom?
Carbon.
Carbon. What should be bonded to that carbon?
Carbon. It's written that way for a reason.
The formula can give you that information. When we talk about GenChem doesn't give you the formula in a way that leads you to the structure. OChem does. Okay? There are some notations that are more obvious than others. That comes with practice. Okay? So follow the formula to help lead you to that answer.
What is that called? CH235.
An acylium ion, okay, or the acetyl carbocation. I think acylium ion is what you're going for on that. Okay, so between those two structures, which one's correct?
Both of them.
They're both wrong. What's wrong with the top one? As a hint, the answer is on the screen. Octet rule. When we look at that structure, does that positively charged carbon have its octet satisfied? Nope, which means it is wrong. What I would need to go through and draw is the structure where, and this is where everybody freaks out, that is awful. You can't do that. Oxygen can't have triple bonds. It absolutely can. Yes. Welcome to OChem. What would the charge be on that oxygen? A positive charge. What? Oxygen can't have a positive charge. Yes, it can. Which of these two structures is the better Lewis structure? The bottom one, because we've satisfied octets and we've minimized charge as much as possible. Why do you not like the bottom structure? Okay. So there was an option for triple bonds. Oh, that looks ugly. Triple bonds don't look ugly. Don't be judgy.
You've got a positive charge on an electron.
I have a positive charge on the second most electronegative element on the periodic table. That just screams horribly wrong. That does not change the fact that according to our rule set, this is the best Lewis structure. Okay? I did a little bit of erasing, and we look up at the top, what do we have? Best. Ooh, versus useful. The top structure that we drew, while that may not be the best, is probably the most useful. Okay? Because when I think about that formula and how that compound reacts, guess what atom reacts? The carbon. Okay? Using the first worst, or the least, there's no nice way to say it. I usually reference this as the first worst Lewis structure is probably what you want to use to predict reactivity. Okay? So I want you to hold on to that information because we'll use that a lot. Okay? When you get tested on which of these is the best Lewis structure, hands down, guaranteed you get the comparison between these two. Okay? Almost always. And almost always everybody says that one's the best. It's not the best because that's not the rule. It's the most useful, and that's the one I'm going to use to do a reaction. Okay? But the bottom one is the best one. This happens in a bunch of different places. You have to watch out for it because you'll be thinking about reactivity, not about best. Make sense? You could look at it as like couples. When you go out on a first date, right? Or when you get married, right? When you get married, what does the guy wear? A tux. When is that guy going to wear a tux ever again?
Never calls for it.
Probably never again, okay? Because he's showing the best, but that's not the way he's going to act, okay? And I'm not just calling out guys. Women do the same thing. You wear fancy white flowy dress thing that you'll never wear again too. We dress the best. That's not how we act, okay? So best versus useful. Formal charge versus oxidation state. We talked about formal charge. Formal charge is important. That's where I want your focus to be. Oxidation state or oxidation number. If you think back to Gen Chem, we could calculate that by knowing differing oxidation states. And for a simple molecule, say like sulfate, you could probably go through and predict the oxidation state on, say, sulfur or any one of the oxygens. And that wouldn't be that difficult. But if we move to a more complex molecule, say like the one that we just had drawn up, and of course the pen spun around because I got too excited. When I go through to try and calculate the oxidation state for this molecule, and I'm going to draw the useful one, I'm now going to have a problem. Why am I going to have a problem with this structure? Is the oxidation state and number for carbon identical for both carbons? No. They're different. And when you go through and determine oxidation state the way you did in Gen Chem, you're making the assumption that they're the same. Which means the method that you use to determine oxidation state or oxidation number is no longer useful. There is a way you could go through and do it. It's less used, so I wouldn't stress about it. It is mentioned in the textbook. I might ask a question in the homework about it, but that would be it. Okay? I just want to mention it so that you're aware of what's going on with that. After that, we've got Lewis structure and potential examples. Let's run C3H8O, because we are done. Sorry. Give me a valid Lewis structure on Monday. So we'll do a quiz. That'll be what we start Monday with. I want a Lewis structure for C3H8O. Okay?